All right, everyone. I am here with Shayan Mortazavi. Shayan is a data science manager at Accenture. And Shayan, I'm excited to welcome you onto the podcast.
Oh wow, Sam, it's a pleasure to be here. I'm really thrilled to talk to you, and yeah, looking forward to it.
Let's do it. So, you recently presented at SIGOPS AI and HPC Summit, and we're going to dig into your presentation and some of the work that you're doing there at Accenture. But to get us started, why don't you share a little bit about your background and how you came to work in data science?
Sure. Well, an engineer by background, and I started as a mechanical engineer in energy domain, building structures and pressurized systems in energy sector, oil and gas industry, and then I moved slightly into simulation of the structures and components that are used mostly in the heavy industry domain. And then I got interested into material science and worked a little bit conjunction between the simulation softwares built for analyzing basically structures in that domain and material in terms of the characteristic, the properties, and then through that, I had to work a lot with data and doing a lot of tests and these structures and with their properties and making sure that they are fit for their service and they have good integrity. And so, dealing with a lot of data kind of got me to think about, are there other applications for these data that we receive, which in the engineering domain, it's usually people working with these formulas and these scary calculation chits and softwares and simulations. So, yeah. And then I got excited about using data to solve some of the difficult problems that exist in engineering domain. Slowly moved into machine learning and statistical learning, and then yeah.
Nice, nice. Well, tell us a little bit about your group at Accenture and your role there.
When I joined Accenture, I joined a group called Industrial Analytic Group, and it is a group which is primarily focusing on application machine learning and statistical inference in the heavy industry and resources, what we call, uh,
Hmm.
kind of covering mining sector and oil and gas, and renewables, and uh, every sort of manufacturing base that have some heavy assets. And then yeah, in there we kind of look into multiple different type of problems from um, production efficiency, supply chain, predictive maintenance, and optimization of um, the production plants and yeah, these sort of things.
Got it. And predictive maintenance, which you mentioned, was the topic that you focused on uh, for your talk at the SIGOP Summit. Can you give us a little background on predictive maintenance and, in particular, some of the use cases that you've worked on?
Well, that's an interesting topic because especially in oil and gas and energy sector, because they are heavily regulated, and there are decades of applying best practices into their operations and their maintenance systems. It is kind of there is a inertia and changing or shifting towards more advanced sort of solutions. Um, so maintenance itself as a problem is trying to maximize or increase the reliability of assets. And this can be cars, it could be trucks, could be uh, stationary, static sort of equipment, tanks and towers and drums, could be some rotating machineries, Um, so if the objective is to maximize their reliability, increase their availability and efficiency, um, there has been traditionally a kind of a myriad of strategies that asset operators depends on complexity of the assets and they have applied. Um, Traditional practices like fixed base maintenance, where you let the machine run to failure and then you fix when it is broken. So it's very costly, um, and you don't have any view what is the state of the machine. And then um, there are some kind of more clever, more um, systematic sort of approaches in the maintenance that are called time-based maintenance or scheduled maintenance, where you define a sort of a strategy of how to regularly
Kind of getting a
repair.
sense for the mean time to failure of different components and using that to build up to when the
Exactly,
thing might break. And
absolutely, yeah,
yeah.
these sort of things.
Hmm.
So in the past, let's say 3 4 decades, when IoT and SCADA systems came into heavy industry uh, domain, then a branch of, let's say, preventative maintenance emerged called condition-based monitoring, where the objective is to monitor the health of the equipment at any level using the sensory data they receive, and then use some early warning sort of functionality on top of that to detect any problems at system level or different hierarchy, and then act on top of that. So preventative maintenance under the condition-based monitoring, these CBMs are um, kind of resolved a lot of the traditional issues in this domain. And uh, predictive maintenance is a child of the CBM systems, like the condition-based monitoring, which simply the objective is can we use a fully data-driven system to predict when assets are going to fail in future, and based on that optimize their maintenance actions and optimize over their resources and cost. So yeah.
And so your presentation, long title, a novel framework for predictive maintenance using deep learning and reliability engineering. Uh, so the kind of the broad context or problem that you're working on is predictive maintenance. What was the specific use case that gave rise to some of the work that you talked about?
Beautiful, yeah. So in this work, we try to um, not just fully rely on a data driven machine learning sort of approach, but see how we can combine and marry the domain knowledge exist for decades and been built up with the sort of capabilities we get from machine learning to address this very specific problem of can we detect failures at different levels of these machineries in advance and provide some insights that can be meaningfully taken as maintenance actions in order to move away from like reactive sort of maintenance, or and also to let them to judge whether they can delay the maintenance actions or interventions or shut down of their plants. So this framework was specifically trying to break down the systems, these complex systems, into multiple different levels in terms of the complexity and the functionality in the system, in the entire system, from reliability point of view, and then use machine learning to um, kind of monitor the performance of these little building blocks, and then uh, by by the means of aggregation through the science of reliability, engineering then make sense of what is the global picture. So this framework specifically, yes, was applied into rotating machineries, which we use everywhere in the petrochemical plants and power plants, refineries, pharmaceutical industry, everywhere. And like generators, turbo turbo generators, pumps, compressors, and turbines, these type of things. Exactly. So these are complex. These machineries are you can look at them like the turbo generators as jet engines. They they have a very high RPM, rotating parts, like 20,000 to 30,000 sometimes RPM, like exactly like a jet engine. Lots of moving parts, high vibration under significant loads, temperature, pressure, and yeah, heavily censored.
Yeah, I don't remember the specific stat, but a few years ago, when in the early days of IoT, like there was this Boeing jet engine or GE aircraft engine example that we would throw around all the time, and just how many sensors were in this engine. And it was an astounding number. And so this is all time series data that you're collecting.
So this is an interesting point because these machines are, let's say, in the energy sector, they are heavily censored, um, up to 2,000, 3,000 sometimes, number of sensors monitoring um, like pressure, temperature, vibration, flow rate, some process parameters. But the purpose of these sensors are um, not necessarily to provide maintenance inputs into maintenance engineers. They are there to for safety purposes, um, or to regulate the process. Um, so the and in order to address a problem of maintenance, we don't necessarily have the adequate type location of the sensors in terms of the type of time series that we want, or the parameters we want to monitor, and also the redundancy in the type of sensors that we want to have to monitor specific modes of failures, for example. And also, there is no scope for retrofitting type of sensors onto these complex machines. Um, so yeah, we receive a lot of time series data and we have to apply a predictive solution, which is a kind of new generation approach on top of old fashioned censoring sort of practices. And that makes it a little bit interesting.
It's really interesting that you put it like that. The idea that the sensors that are in these machines aren't necessarily there for you to make predictions from. That it strikes me that that was always left out of this narrative of like IoT and predictive maintenance and digital twins that I've heard over and over and over again. But what you're describing is like you've got all these data points that are being spun out of these machines. You've got a bunch of, you know, many years of equations to predict the reliability of the machines and when you might need to repair them, the whole field of reliability engineering that's evolved. But there's a gap. It's like the bridge was built from two shores and doesn't meet in the middle. And it sounds like that's what the core of your presentation was. You're using predictive models to map from the data you're collecting off of these sensors to the equations that you would traditionally use.
Precisely. That's a very good summary of, yeah, and of the problem itself. Yeah, maybe going forward into future, where the operators and the manufacturers of these machineries, um, realized the necessity of censoring the machines adequately for the specific purpose of predictive maintenance, which I think it's a trend in advanced sort of manufacturing fields, in robotics and machineries which are employing a lot of robotics in them. There are sensors to monitor the health of the machines and parts of that. But in this specific case, exactly to bridge this gap, um, we wanted to really connect the failure mechanics, the knowledge within the failure mechanics, with the predictions from machine learning. And what do we mean by the failure mechanics? So there is a type of analysis in the domain of engineering, of machineries, and structural design, which is called FMEA, failure mode and effect analysis. So what is that? It is basically a procedure to uh, utilize the research and the standards exist to analyze the modes of failures of the machine, break down the modes of failures and the effect of each failure mode onto these specific type of equipments or components from bottom up, and then identify the indicators that can kind of provide a bit of symptom of these type of um, failure modes, and then act on top of that. So this is a very rigid structural engineering practice that is performed in the beginning of the design or operation and then gets updated. So we were thinking um, the kind of the novelty of the thinking that maybe we try to deploy was, can we use this failure mode and effect analysis and um, build a sort of matrix that from all sort of information you get at component level, um, we provide a kind of more insightful picture of what can go wrong, these building blocks of the machines. And then again, by the use of the reliability engineering concepts, how we can combine these information at these building block levels and make sense from maintenance engineering point of view what is going on at higher hierarchies like assembly levels or at system level. So yeah, this was the perhaps the core novelty of the approach.
And so the this matrix that you described, is that part of the traditional way of solving? Like, is that the input to the traditional reliability engineering approach, or is that artifact of the solution that you've applied using deep learning?
No, this was, let's say, one of the pillars of this approach. This didn't exist. So the FMEA does exist. This failure mode analysis, the kind of cause and effect relationship mapping, which you may in like data science domain use different approaches like Bayesian approaches to map or build the causal mapping of the system. But in our case, we adopted the cause and effect maps from engineering domain, and we built something called fault matrix. And this fault matrix is a relational matrix, a map between the failure modes and really the sensors. So in this matrix, what you have is a map of what are the importances of each sensor in terms of redundancy and the influence in ability to detect some of the failure modes at component level. So this is can be very static matrix in terms of the importance relationship between the sensors and failure modes, or it could be learned a matrix, or it could be probabilistic. So each, let's say, importance factor in terms of sensor to failure mode could be kind of incorporating uncertainty um, through the means of probability density functions.
Got it. Got it. And so going back to the long title that I mentioned, where does deep learning come in?
One of the first steps of kind of detecting the problem um, is still an open question for us. How we can detect accurately the problem and then link it to um, an understandable um, mode for engineers. But to detect it, I think um, traditionally, at least in the field of condition-based monitoring, people have been applying some fixed thresholds onto sensors, and then by this means of like operating bands, they were able to detect anomalous behavior, and then based on some rules, act upon those anomalous like sequences or so on and so forth. In our case, through some literature review, um, we wanted to see, can we predict the behavior of these machines um, in their all possible states? So these machines, as you know, they are operated in multiple different modes in terms of operation, depends on how much load they want to apply to the machine. And also because they are in operation for 30 years, many several hundred thousands of hours in operation, they see multiple different changes in the state of operation in the entire asset. For example, in oil and gas industry, the reservoir pressure and temperature depletes, the regime of operation changes. So whatever sensor reading that you receive from these all parts of the machines is subject to shift or drift or change. So setting a fixed, let's say, set of thresholds on these first would require continuous maintenance and observation of the false alarms and so on and so forth. And also, it may not be fully kind of aware of all possible modes of operation. So we were thinking, we haven't seen everything of these machines' operations. Should we use machine learning to learn from the past of these machines? Do we know the entire state of the data? The answer was no. We were in the best case, we only knew 10, 15 to 20% of the entire operational state of these complex machine sensor.
Do you mean 10-15% of the operational state as defined by a specific set of sensors over a lifetime, meaning you have the 10% of the lifetime of the machine, or that the sensors themselves only capture some small percent of the operational state of the machine itself?
That's a very good question. I think it's exactly the combination of both. Um,
Okay.
if there is a machine which has been just in operation, you can have some prior belief about how the sensor should behave or how we should receive the data, but the rest is mystery. And
Hmm.
often, two identical machineries have different sensor readings if you start them at the same time, even set up on the same plant. So this is one side of the unknown uncertainty, and also a lot of operational modes, as you said, in terms of the state of operation is unknown throughout the life of the lifespan. Other thing is, the more interesting one is the failures, um, the patterns of failures, the trends. In majority of the cases, when you want to cover the entire, let's say, um, 200 or 300 different individual components of these machineries, you haven't seen failures of a lot of these components in their life. So to maximize the coverage, and also not make rigid assumptions. You have to move away from traditional supervised type learning uh, to detect failures. That doesn't work, or if it works, it covers maybe 5% of the problem. So, where did machine learning and deep learning came to help us was we said, okay, let's say, do we know what is, into our best of knowledge, what is the temporal, transient, healthy behavior of these machines and the sensor observations that we get? We said possibly yes, we have good knowledge of that to some degree. And then we said, okay, let's build these models, which in this case we used recurrent neural network LSTMs at sensor level to monitor and learn the healthy behavior or kind of sequences of these machines. So from what we get in terms of the sensor live stream data, let's say if we build this representative model of the sensor from purely healthy behavior point of view, can we predict a healthy vector into future? And then checking that sort of sequence of time series versus what we actually receive, we were able to predict any deviation. So yes, this kind of uh, difference or residual signal for us was the outcome of using machine learning in the case of recurrent neural network LSTMs to detect abnormalities.
Got it. Got it. And so to play back at least one part of that, you started talking about the traditional approach and like setting these thresholds, like you might see in other places where you would use anomaly detection. And one approach might be to like automatically set the threshold, but that's not what you did here. What you did is create maybe a lower level or a kind of a richer model of the machine itself, and didn't use a threshold based approach. You use this more residual based approach to determine when an anomaly was happening.
Exactly. So um, basically, this detection of abnormalities was the first sort of step, let's say, in this workflow. As soon as you detect some sort of abnormal or outliers within your residual signal, which is the error signal, then what we could do was to use some parametric sort of techniques that you build a distribution of what is your error signal and then set some parameter around the distribution, and whatever goes out of the sort of the threshold bands, you detect them as abnormalities. But again, we found we don't know a lot about these signals. This is going to produce a lot of false alarms. So what else is out there? So we got into this novel approach that scientists in NASA kind of developed and applied to their telemetry data received from the space shuttles, which is called non-parametric thresholding. It's a kind of a dynamic non-parametric thresholding. And what is this? Is basically trying to fit a dynamic sort of set of bands around your residual error signal, and then um, these dynamic bands then allow you to detect um, any sort of abnormalities or outlier sequences um, that sort of is more robust in terms of not reacting to sort of temporal behavior of the sensor data that you receive, has some cushioning sort of kind of buffer zone to um, prevent false alarms. And also, it is able to, with the help of LSTMs, to capture multimodal operational phase, like the heterogeneity in the data. So the technique itself is very simple but kind of beautiful technique. It is at any given time uh, define a wide range of threshold bands and then try to maximize the criteria by analyzing the whole historical distribution of the error. And then that criteria is, can we detect any sort of new set of observation that can um, deviate uh, the properties of the error distribution most at any given time. And that set of band is set as the new threshold dynamically. So once you have this set of thresholds, then you detect the strings that sits outside of the threshold, and then you calculate a score for the sequence. And that score itself is calculated based on the second moment of area of the sequence outside of the threshold band.
Got it. Got it. So you mentioned in their LSTMs, that's the way that you're modeling the state of the individual components.
Sure, yeah, exactly. So the use of LSTMs was to um, exactly to what sort of algorithms are out there that can um, understand the temporality in the signal and the multiple modes and provide the best representation of these noisy sensor readings. Um, so in our case, it was very important for us to um, make these predictions in future of the healthy beat pattern by understanding the kind of the historical changes in the signal. So long-term, short-term memory type signals allowed us to kind of use the previous states of the system and incorporate that because of the specific architecture of these algorithms to provide a correct representation of the signal. And it was very expensive to build LSTMs at sensor level. So we talked about few hundreds and few thousands of sensors per compressor. For in our case, we had to monitor about 200 sensors or 100, 200 sensors per machine. So building um, these number of LSTMs and optimize them based on few years of time series data with high sampling rate was a challenge.
One question that I have about that is the you mentioned that each of the LSTMs is mapping to a sensor. The It's kind of like you have a hierarchy, right? You've got these sensors. These sensors presumably map to components, and the components map to whatever the machine is. Um, I guess the reason why you do it at the sensor level is because you really don't know the relationship between the sensors and the components per se.
A very good point. Because we adapted this reliability based system, which is aiming to detect the modes of failure that are active at any given time, we had to um, go to a bottom up approach. We had to utilize the entire sensors that are monitoring one component. Let's say in a compressor, we have shafts, we have bearings, we have um, seal systems and impellers of the compressors. So let's say in a bearing case of bearings, you have bearings on either side of the shaft, and you have multiple different sensors monitoring the behavior of these components. A bunch of temperature sensors, a bunch of flow rate that are injecting lubricants to the component, a lot of vibration type sensors in multiple different directions. So making sense of these of the active failure mode at any given time is a complex problem. We had to understand what sort of abnormalities working together would relate to which failure modes. For that, we needed to know abnormalities at bottom layer, at sensor layer.
You created these kind of models or representations of your sensors and the I'm trying to put the pieces together now. You've got these representations somewhere in the middle. You're trying to get to the fault matrices, and then you've got on the other side of the fault matrices your traditional reliability engineering equations. How do you get from the LSTM output to the fault matrices?
Yes. So I think the keys LSTMs are providing these uh, healthy sequences of healthy behavior
Hmm.
as a kind of mimicking the the machine behavior from healthy point of view.
Is this where the
Then
non-parametric came
yes,
in? You've got
when
this, and go
yes,
ahead.
so the by by creating this residual signal or error signal and
Hmm.
then applying the parametric thresholding or non-parametric thresholding on top of that, um, from by comparing the healthy from actual,
Hmm.
then you calculate a score, what we call anomaly score, let's say at sensor level. So at
Okay.
any sequence of time, at any time stamp, let's say, you have an anomaly score at sensor level. So feeding an anomaly scores from 10 sensors related to one component into the fault matrix or this uh, cause and effect sort of matrix, then you get a score per component per failure mode at any given time. So this is, let's call it like component defect score or failure score. And then having all of these failure modes lined up and components accordingly, then you can have a representation of a ranking of what are the anomalies at any component level. And then, as you said, by the use of the reliability engineering logics, you can aggregate the scores at component level, let's say lots of different bearings and multiple different seal systems together and aggregate their abnormality scores together, um, and then roll it up into the assembly level. Then
Hmm.
you can aggregate again at assembly level into the system level, which is compressor. You can follow the same and go and cover your entire asset.
By entire asset, we're talking about like a gigantic oil rig or something.
Exactly.
Have you
Yeah.
gotten that far?
We've gone up to critical path machineries. And
Okay.
critical path machineries means those which are sitting on the critical production line.
Hmm. Hmm. You've talked a little bit about the kind of the challenge of just training all of the LSTMs that are involved in doing the kind of modeling here. Can you elaborate a little bit on what some of the biggest challenges were?
Well, LSTMs are not easy to train and optimize, um, especially that we are dealing with quite quite a lot of data. We're talking about 1 second sampling rate of few years of one sensor, and when we talk about thousands of sensors, it's quite extensive. So LSTMs have multiple different hyperparameters, and to get the best results, you have to really invest time to optimize them. The other thing was we are dealing with multiple different type of parameters. We want to build these representations. Vibration type sensors are very different in terms of the noise patterns and temporality. and the conditional dependencies historically to what has happened in order to build a more accurate representation in the future, uh, as opposed to, for example, temperature type signals, which are they have a big delay and there is not much temporality in it. The noise characteristic is different. So optimizing LSTMs at these sensor levels was a challenge, and for that we were lucky to collaborate with SIGOP, which is kind of the black box optimization platform, and then that helped us a lot using the Bayesian type optimization to quickly learn the optimization of parameter space very quickly and efficiently, because there we have the ability to optimize over multiple different objectives. Training time was one of our main objective, as well as mm, reducing the loss.
You just said something interesting. The optimization problem that the way you ultimately frame your optimization problem wasn't solely constrained to system level criteria, but you also had this, was it a train time criteria or compute train time?
Yeah, exactly. So I think this is a complex sort of pipeline of connected pieces together. Performance of LSTMs in order to detect healthy pattern, patterns or sequences, and detecting the residual or error, and feeding that into the kind of this cause and effect matrix, and calculating the scores and evaluating these is entirely together is one massive optimization loop. So you can look at the LSTMs itself in and optimize the hyperparameters there, but getting the best fit there may not necessarily give you a global optimized path. So you may get into a local optimization here. So connecting all of these together and building this uh, gigantic sort of optimization loop with multiple different hyperparameters, which are not necessarily all from coming from the LSTM sort of hyperparameters, was a big challenge.
And not, so not just from the LSTM, but not just from a single LSTM. You've got parameters from multiple LSTMs, say 50 or 100, plus these kind of broader constraints on um, your runtime. Was your accuracy represented as a threshold or a constraint, or how did you incorporate that into your optimization?
The ultimate um, kind of objectives were into two different um, dimensions. We had to have the human in the loop in order to evaluate the entire optimization. And that was what is the intuition and engineering domain knowledge in checking whether an abnormality score at system level or assembly level is really an abnormality based on their experience and their knowledge of failure mode analysis. So that was our ultimate objective, that let's say we introduced a bit of supervised sort of training into the loop. So we had a bit of labeling going on here in terms of what is this ultimate score at system or assembly or component level. And then we had multiple hyperparameter sets at LSTM stage, at the scoring calculation stage. And so yes, we were ultimately optimizing over the frontier of reducing the false alarms, false indications, and maximizing the correct detection per failure mode. So that was our frontier.
Can you elaborate a little bit on the human in the loop aspect of that? How many, how much labeling had to go into being able to build these models?
That's a very good question. I think we built some blueprints in
Hmm.
hours and hours of discussions with lead rotating machineries, those who have spent designing these machines for 20 years, 30 years.
Hmm.
So we had lots of workshops to go through these patterns, historical patterns of past 10 years or so of the machine operation, and then um, get all of these experts in agreement of what is their final judgment of which sort of sequences are abnormal sequences, which are kind of noise artifacts, which are sensor drifts, and so on and so forth, which of them are combined together are representative of failure mode. So through that process, we labeled several of these examples, and then it was a labor intensive process for sure. But in
And
order
to be
to,
clear, what you're labeling is a time series data set from of what? All of the sensors in a given machine or a particular sensor, or I guess it would have to be system level,
it has to
right?
be at some level, yeah. So we covered I think 15 or 20 critical components of these,
Okay.
let's say, turbo compressors, which are sitting on the critical path of the machine itself. Failure of each would result in the failure of the entire machinery, downtime. So we identified those and some high critical failure modes that statistically or from reliability point of view resulted in majority of the failures. And then we focused on that.
And ultimately, what the SIGOPT element of the optimization process was kind of narrowing in on the points on the frontier that you had to care about, and optimizing across that, so you weren't trying to optimize across the entire state space of hundreds of LSTMs and these constraints and all that stuff. Is that the general idea?
That's very true. Yeah. So hyperparameters that we're talking about are like the learning rate and the look back sequence, which in the case of recurrent neural network is important. Also increase the training time, the, and regularization parameters, and so on and so forth. Um, it was about 12, 15 number of hyperparameters per LSTMs to optimize, and multi-objective, basically multi-metric optimization. So using the Bayesian optimization definitely helped a lot to quickly reduce the space of exploration.
And so what's next for this effort?
Sure. Um, it's very exciting actually. So what we talked about today so far is primarily focusing on one aspect of, let's say, predictive maintenance domain. There are multiple different things you can do. If the main objective is to make the best maintenance action, this is a very difficult question to answer, because detecting problem is one thing, making an action and a correct action is other thing. And the action space is influenced by what sort of resources do you have available, which part of the geography you are operating. Are you in an island or an offshore, 200 kilometers away from everything, which supply chain complexity, and the complexity of the maintenance team and the maintenance tools that you have to have on board, the lead time of the components that you need to order and being built and tested to come may take 10 months or 12 months to come.
So you're saying that you've solved the easy part of the problem so
That's
far.
correct. That's correct. This is a very complex question to answer. So, what other things that can help in terms of prediction side on this first aspect before getting into prescriptive sort of
Hmm.
side of maintenance is how much time do I have to fail till ultimate failure? This is a very valuable information. So we talked about, I think, a lot of off-the-shelf tools that you see existing in the market, the GE tools and so many other things are very good in detecting the anomalies, but detecting what how much time do I have at at component level and failure mode, kind of from that point of view, is very valuable because it allows them to safely operate their systems without shutdown, because
Hmm.
these machines are not designed to kind of constantly shut them down to repair or do some interventions. So yeah, predicting time to failure is and linking that to the knowledge of um, failure mechanics is an interesting topic.
And then you get to take on the what to do about it.
That's very true. Yes, and I think there have been a lot of efforts into research, and also beautiful tools exist at the moment, which are trying to optimize the action
Hmm.
over cost, over resource availabilities, and over health. So health sort of, let's say at system level, health plot or health indicator can come from these sort of approaches: anomaly detection, time to failure,
Hmm.
aggregation at system level. But understanding the cost, this is a whole set of, new sort of formulation of what is the my cost function from operational plan point of view, the the revenue that the system is generating, the criticality, so on and so forth, to build this cost function. And then resources also is also in majority of the cases is human related. Um, and we are talking about the materials like the spare parts point of view, and also human repair experts who are going to be deployed onshore or on site or offshore, kind of um, external supply. And building a function, mathematicizing that is a task.
Hmm. And do you expect to be able to apply similar ideas, meaning introduce machine learning or deep learning to complement existing domain knowledge, to solve those other problems as well?
Definitely, definitely. I think a series of like probabilistic approaches, Bayesian based and Bayesian networks, for example, or even a lot of machine learning applications in predicting different aspects of their cost function in terms of the supply chain, representation of the supply chain as a kind of a sequential model. And also reinforcement learning can come into effect in building the function of your and learning your cost function and supply chain. Also, a lot of NLP people are applying in kind of feeding into sort of knowledge graphs, and um, by building these knowledge graphs, you can link the entire asset data in terms of the operational plans, what is going on in terms of the in and outputs, and then driving information kind of from these knowledge graphs and feeding that into some sort of analytical layers to predict what is the consequences of actions um, on top of these knowledge graphs is another thing.
Got it. Got it.
Yeah,
Awesome. Awesome. Well, Cheyenne, thanks so much for taking the time to share a bit about your experiences in this area. Very cool stuff.
pleasure. That was pleasure talking to you. It was good
Thank
fun.
you.
Thank you.
Thanks.